Next, let me very quickly review the motivation that I had used in the previous sequence, the motivation to really demonstrate why the small signal model can be really useful for us. So in this motivating example, I was looking to transmit music over a light beam. And I had this device that I called the light emitting export beam, a hypothetical device, which had a nonlinear characteristic that looked like this. This was the VD, and this was ID. And I was looking to transmit music in a linear manner over that device. So the construction is the following. Let me very quickly review the construction. I have an input voltage VI. Think of this as my music signal, and that falls directly across the LED, which produces some light intensity, which impinges on the receiver, which is a photo receiver, and that then produces a current IR, which is amplified and produces music at the output. And everything would be fine, just that this conversion from VD to ID was nonlinear. And because that was nonlinear, I got a lot of distortion in my music. So my goal is to try to get this transfer happening in the linear way and get a linear response out of the system. So how do I really go about doing this? Let me just very quickly also review the kind of waveforms that you get when you have a nonlinear device in the system. So as an example here, let me continue with the same motivating circuit. And here's my IV characteristic of the LED. And let's very quickly look at the kind of curves that you see with this. And again, this is just a review of what I covered the last time. So if I plot ID versus time, in this case, suppose my ID, if I plot VD versus time, a VD here is a nice little sinusoid. And when I when I look at how the VD gets converted to ID, I can do the following construction that I showed you last time. As VD has excursions in voltage, those VD values can be plotted at various points on the x-axis related to the IV curve of the device, and I can find corresponding values of ID for each value of VD. For excursions of VD as shown here, I end up getting an ID as shown on the left-hand side. Notice that the ID characteristic, that ID looks quite a bit different from VD, and that's because of the distortion happening not only because my ID versus VD curve is nonlinear, but also because of this flat region here in the on the negative VD axis. And because of this, my ID ends up looking very much unlike a sinusoid, and that gives rise to a lot of distortion in the circuit. I thought I'd do a fun little demo for you to show how I'm constructing the output given an input, where the input falls across across my device VD, and I get the output as the current produced by the device. So here's the construction that I'm going to do. I plot the ID versus VD characteristic as before, and here I'm going to plot VD on the where the time axis is going down like this. And so VD is plotted such that the VD axis here is parallel to the VD axis of the transfer curve. And then, as before, I'm going to plot the ID curve with time going to the right, and my ID axis parallel with the ID axis of the transfer curve. So let's see. Let me do a fun little animation to see if I can show you how things work. I expect to see as an output this curve for ID. And I had a bunch of fun with PowerPoint, and let's see if I can make PowerPoint talk to us and show us how I got this ID from VD in a manner that is about as clear as it gets. So for example, if you look at this blue point here, this corresponds to t equal to 0 and VD equals 0. So that point corresponds to VD equals 0 and ID being up slightly above 0. And it corresponds to time t equal to 0 here, and an ID being slightly above 0. So these 3 points, call them P1, P2, and P3, are related in the fashion that I just mentioned. So watch those 3 points, and I've built an animation, think of going berserk with PowerPoint, built this animation, and take a look at how, as the voltage VD changes as a function of time, how ID will change as a function of time, and take a look at what part of the VI characteristic of the LED is articulated by the changes in VD. Okay, so pay close attention and have some fun with PowerPoint. So as the point moves along the VD curve, and then we have the corresponding value moving along on the ID. Okay, let's stop there, and then let's get right down to the small signal model.